So the first part is about generalities on indoor positioning solutions. So, as I said, outdoors you have the GPS and so, while indoors you have no line of sight between your mobile device and the satellite due to multipath diffractions and so on. So you have to rely on other systems or devices, such as short-range communications, GNSS repeaters, infrared devices, accelerometers or RFID, and so on. So, first solution is to use cell positioning, which can be used in 2G, 3G, 4G, Wi-Fi, Bluetooth networks, and so on, by using the access routers of the device to the core network. So the access routers may be the BTS, the access point, the Bluetooth devices, and so on, whose coordinates are known. So you approximate the mobile device location by the one of the access router. The advantages of such systems are that they are very simple, so you know and you register the access router's coordinates, and you look the association between the mobile host and the access router. Then you infer the coordinates of the mobile device as being the same as the coordinates of the access router. There are also drawbacks. It's not accurate depending on the network type. So for GSM, which is the 2G, you have several hundred meters to several kilometers error, while for Wi-Fi you have several tens meters error, which is not sufficient if you want to provide an accurate location inside a building. You can also rely on ultrasound systems such as ActiveBat and ActiveBadge and Cricket, which combine ultrasound and radio signals. So the radio signal whose speed is equal to the light speed will initiate a timer. Then the ultrasound whose speed is far slower, 340 meters per second, will stop the timer. Since the radio propagation time can be neglected through the short distance between the transmitter and the receiver, the sound time is used to compute the distances and then the location. It's similar to the GNSS operations. So the advantages are a very good accuracy within 10 centimeters error, while the drawbacks are the cost and to require a dedicated device to be able to locate a mobile device. Now for infrared systems, you can use infrared communications which are available on personal digital assistants and some phones, and which are a very short range, several meters. You use infrared devices as beacons in known and critical locations such as doors, and you approximate the terminal location with the beacon one. The advantages are to be really simple and accurate, so it's based on it's quite like the cell positioning with a very short range. But the drawbacks are that you require a lot of devices if you want to locate in a lot of positions, and you require a line of sight between the devices to be able to transmit and receive infrared signals. Now for the RFID systems. So RFID stands for Radio Frequency Identification, with very short range, passive tags and active readers which induce current on the passive tags. It works as the infrared system with tags on the terminals and the RFID readers which are at known and critical locations. The advantages are still to be accurate and simple, while the drawback is the cost of all the active readers and the number of devices required. Dead reckoning is a completely different system and method. So it's, for instance, used by aircrafts and ships prior to GPS, and they still have these capabilities to be able to locate precisely in the short term. So from a known location, so you have to have the first location, you use your knowledge of speed and direction. and you infer a probable location from this. You get the speed and the direction from the accelerometer, which gives the acceleration, and the gyroscope, which gives the angular direction. So with both, you can build an inertial measurement unit, IMU, which gives you all the data required to be able to locate yourself. The only drawback will be to have an error which is cumulatively higher with the time. Now let's talk about Bluetooth beacons, which are based on Bluetooth 4 BLE, Bluetooth Low Energy, standardized by Nokia to provide an energy efficient Bluetooth. So based on this BLE, Apple provided a new protocol named iBeacon to be able to provide small beacons with long battery life provided by many vendors and with API available to use that to locate some devices. So here is an example of one beacon, which is an ST mode. Unfortunately, these iBeacons are discontinued since they did not work, not technically, but commercially it did not work enough for Apple to continue supporting it. Now let's talk about the main focus on this course, which is Wi-Fi. It is widely spread over the world with private access points as well as hotspots in train stations, airports, shopping malls, and so on. It provides communications with positioning functions if you use Wi-Fi to position the device, and it provides a high throughput able to deliver multimedia services. So when we are dealing with Wi-Fi systems and positioning systems, we want to study several properties to compare these systems between one another. So first is the symbology. It's the location representation. So it might be the presence in a room, so it's discrete symbology, or coordinates, which can be Cartesian, global, WGS84, and so on, which are continuous locations. We also want to talk about accuracy, which is the error between the estimate location and the real location. So if you are using the symbology coordinates, it's a distance between both coordinates, while for the presence in a room, it would be the percentage of good detections. Then we have the positioning rate, which is the number of locations computed per time unit. It's kind of a frequency. The higher, the more devices can be located by the system. It might be bound but not similar to the positioning delay, which is the time between beginning of location computation and its result. It may be related either to calculations required or for the time to gather data. So it does not necessarily impact the positioning rate. You may have a high positioning delay with a high positioning rate just if you need a lot of prior data to compute the location. Then there is the scalability, which is the ability for a system to handle great problems. In indoor positioning systems, that means that you are able to manage many devices, to provide locations for many devices over a large area. It might be one of both or the two of these. Then you have one key point, which is the global architecture, which might be centralized. It's easier to maintain, but it scales less. Or distributed, which is harder to maintain, but scales better. Then there is the topology, which means how much the buildings, furniture, and people are modeled into the system, which actually is a trade-off between the most accurate model and the amount of calculation. And you have to identify what is systemic and what's random in your statistical errors in the measurements you use for the positioning system. Then you have the cost of the system, which might be considered through three point of views. So energy consumption, especially for the mobile devices which run on batteries. In terms of work, it will define how many people are required to deploy and maintain the system. And in terms of money, for the hardware, for the people, for the energy, and so on. So this was the first part with the global overview of the indoor positioning systems and a bit more information about Wi-Fi positioning systems, which will be the point of the next part of this series of lectures.